First thing we want to do is take the antiderivative of the function. So what I might do is expand that out. As I expand it out, interval does not change. And if I take x plus 2 times x plus 2, FOIL that all out, get x squared plus 4x plus 4. So I rewrite the function by expanding out the binomial, and now I take the antiderivative of the resulting function. In doing that, add 1 to my power of 2, get 3. Reciprocal 1/3 goes to the front. Got a power of 1 here. Add 1 to that power, get 2. Reciprocal of 1/2 gets multiplied to the 4 in front. So that's plus 2x squared. Got our constant here, 4. So attach on the x. That's the antiderivative of the function. But we still have an interval here we need to acknowledge from 0 to 5. And at this stage, we take our 5 up here at the end of that interval, we plug in for our x's. We get whatever that value is, and then we subtract whatever we get when we take 0 where this interval starts and plug in for x. Now obviously when I plug in 0 here, I've got x's in all the terms, so we're just going to be subtracting 0. As long as I can calculate out this portion, we could say round off to 3 decimal places, got my answer. Okay, before we take the antiderivative of this function, got the cube root of x, which we know is x to the 1/3. We've got a product here where we probably want to multiply things out. So our definite integral, as far as the interval is concerned, stays the same. We're taking this x to the 1/3, we're distributing through. We're adding exponents as we go, so we've got x to the 4/3 when I take x to the 1/3 times x to the 1st, minus x to the 1/3 when I multiply that 1. So this is the function we want to take the antiderivative of with respect to x. So for x to the 4/3, add 1 to the power, get x to the 7/3, reciprocal of 3/7, moves to the front, minus, add 1 to the power here on the x to the 1/3, get x to the 4/3, reciprocal of 3/4, goes to the front. Still have to acknowledge the interval we're working on, which is 1 to 8. And now, just like the last one, plugging in. So 3/7 times 8 to the 7/3 minus 3/4 times 8 to 4/3. Then we're going to subtract. We're going to take 1 and plug in for our x's. Of course, we plug in 1 for our x's. We're taking 1 raised to a power. It's just going to be 1. We've got 3/7 minus 3/4. Feel free to check me on that. All right, we start with a product on this one. However, this is not one we can multiply out. Recognizing this root here and the 16 minus x being raised to 1/2, that is significant. But also recognizing that we're going to have to let u equal 16 minus x, that's equally significant. So I'm introducing the new variable. That means I'm setting up the new problem. Now I'm going to hold off on my interval for just a second, because remember, if you introduce a new variable, you got to set up a new interval over here. All right, u is replacing the 16 minus x. That's under the root. So over here I write u to the 1/2. That takes care of this piece. The pieces that are not accounted for, the x and the dx, meaning we take the derivative of this equation right here, which is du, equals 16 goes to 0, negative x goes to negative 1 dx. As far as what I'm trying to replace the x and the dx. I at least have a dx here I could replace if I divide the negative over. So taking this dx out, I replace that with a negative du. I'm going to leave myself a little space here because I still have to account for this x. So this is where we go back to our u equation. We solve for that x we need to replace. So if I solve for x here, well, basically I could add x over, subtract u over, right? X would equal 16 minus u. So I insert that in over here as a quantity. As I mentioned before, we changed the variable, so that does change these interval values with regards to what we're working in terms of. We're working in terms of u now instead of x. So these were x values. I need to plug in down here to figure out the corresponding u values. If I plug in 0 down here, I've got 16 minus 0, which is 16. If I plug in 7 down here, I've got 16 minus 7, which is 9. And something should stand out about that, right? They're not going in the right order. So that's not a big deal. We can switch them. But when we switch them, we have to change our sign. So normally I'd negate in front of the integral here, but since this is a negative right here, we'll just make that positive. Okay, still some cleanup to do, even though we've improved upon the function. We've got our definite integral now on the interval 9 to 16. We can distribute that u to the 1/2 through, so it'd be 16u to the 1/2 minus, got a u to the first there, add our exponents, be u to the 3/2. So I'm going to take the antiderivative of that function with respect to u. When I do that, adding 1 to my power here, I've got u to the 3/2. Reciprocal is 2/3, gets multiplied to the 16 in front, 32 over 3. Minus, got u to the 3/2 here, add 1, that's u to the 5/2. Reciprocal is 2/5, bump that to the front. Still have our interval here, 9 to 16. Okay, at this point, we're ready to calculate because we're going to take 16, we're going to plug in for u. Whatever that gives us, we'll then subtract off, take 9, plug in for u. Spilling off the page here. All right. Check me on this, but I got 82.27 as an approximation. What are we going to do first here? It's got an E, no big deal. Yeah, what's U going to equal? X squared plus 5, okay. Whatever the exponent is up here on that E. So we introduced the new variable. We set up the new problem. We're letting u equal the exponent on e, so over here I write e to the u. That takes care of this piece. I still need to account for 4x and the dx. So I take the derivative here. Got du equals 2x dx. I would rather have a 4x dx, so I'm going to multiply both sides by 2. There's my 4x dx that I'm looking for, so over here I can insert in a 2 du. Got the new variable, so we need a new interval to work on. Take 0 here, plug it in my equation for u. Let 0 be the x part, right? 0 squared plus 5, get 5. And And then plug in 3. Got 3 squared, 9 plus 5. Got my new and improved problem, right? At this point, if you take your antiderivative, 2 is just coming along for the ride. You're taking the antiderivative of e to the u, which is e to the u. Acknowledge the interval that you're working on. And insert for said interval. And you can calculate out from there, but for all intents and purposes, that's a solid answer. It's very precise. If it was just cosine of x, we'd be good to go, right? That pi is causing an issue. Since it's one trig function, whatever's following the trig function, the argument of the trig function, that's going to be what we let u equal. So replace pi x with u, meaning new problem is going to take on the form where we're integrating the cosine of u. Now that takes care of this piece right here. We still have to account for the dx. So take the derivative of your equation. du equals pi, just a number, times x. So if you take that derivative, it's going to be pi dx. Right, had that been 2x, then it'd just be 2 dx. 3x be 3 dx. You're trying to replace dx, so divide the pi over. Dx can be replaced with 1 over pi du, so insert that in over here. Need to adjust for your interval, right? We've got 0 that we've got to plug into this equation. Got pi times 0, which is 0. Got 1/2 that I have to plug into this equation, so pi times 1/2 is pi over 2. Taking the antiderivative of 1 over pi cosine of u. Well, 1 over pi just comes along for the ride. What is the antiderivative of the cosine of u? Just sine of u, right? Check yourself by taking this derivative. Does it take you back there? It does. All right, interval we're working on is 0, pi over 2. At this point, we plug in pi over 2 for u. And then we subtract. We plug in 0 for u. Time to calculate that out. Our answer is simply 1 over pi. Trying to find this exact area bounded by this curve in the x-axis. We need an interval to work on. So you could graph it out. One of the things we should know about this graph is that with it being a parabola, it's going to open downward, right? So at some point, it'd be really nice to see what the x-intercepts are. Right? See where it's crossing the x-axis, because if this is going to be the exact area beneath this curve above the x-axis, it would make sense to find those points. When you find x-intercepts, the rule is y is going to be 0 at those points. So yeah, we could graph it out. You could find the points from the graph, or you could just let y equal 0. Set that equal to your quadratic and solve for x. All right, in solving for x here, probably want to do some factoring as far as a greatest common factor is concerned. Take out a -3. If I take out the -3, I'm left with x squared, be minus 8x, and it would be plus 12. -3, no x attached. We could divide -3 to both sides. It would go away. leaving us with just the x squared minus 8x plus 12 to factor. So if I factor that down, it would be minus 2 minus 6. So where this is crossing the x-axis, it's crossing at 2 and it's crossing at 6. Meaning if I set up a definite integral now based on the interval 2 to 6 and I apply it to my original function, if I can evaluate that integral, that will give me the exact area here. So this one's set up and ready to go. Taking your antiderivative here for negative 3x squared, we know we're adding 1 to that power. We get x cubed. We know that reciprocal is getting multiplied to the negative 3 in front, meaning all that's left is a negative 1. Plus, got x to the first here, so that's x to the second. 1/2 gets multiplied to the 24, making that 12. Minus 36x. Interval we're working on, 2 to 6. So as we've been doing all along here, take this value here, plug in for x. Negative 6 cubed plus 12 times 6 squared minus 36 times 6. We'll get whatever that is, and then we will subtract. Take 2, plug in for these x's. So 0 minus negative 32, final answer would be 32. That's our exact area. Okay.